Hi everyone, so today I shall be introducing you to a new type of differentiation. It's probably different to what we've done so far, but really the kind of underlying ideas behind implicit differentiation is just kind of mixing algebra with calculus. So what is an implicit differential? And now first I want to kind of discuss what's an implicit function and what's an explicit function. So an explicit function is a function where if you know x, you can compute y easily. So for example, y equals x squared means that if we know x, we can just square it and then we have y. But then an implicit function would be a function where you can't calculate y using x. So that basically means you have an equation there, but it's not in its solution form. So something a bit like y plus dy over dx equals x squared. You really can't find y using that because you have that dy over dx. So then how do we differentiate functions which are not explicit? Implicit functions, and the reason I'm showing you this is because actually implicit differentials can be used in all sorts of forms. They do kind of resemble differential equations, which I'll show you later, but other than that you can find inverse functions using implicit derivatives. So that's really cool. I'm just going to show you how you do that. So as you do in algebra, you need to apply some sort of operation in both the right hand side and the left hand side. So we're starting with this kind of circle graph here, which is implicit because again you can't find y just by knowing x. So what you do is you start with the equation of a circle, and that's like a classic example for implicit differentiation. And then you apply an operation on all sides. Now, which operation can we do to simplify this? Because there's a lot of squares, and you know it's hard to do anything using that starting point. So what do? We can apply the derivative operator on each one of them. So on all sides. So that means this. I mean, we can just apply the derivative of x squared plus y squared and then do the same thing in r squared, but I'm showing you that because we know the addition rule and the subtraction rule, we know that we can just work those out independently, and that will be much neater. So if we apply the derivative operator to y squared with respect to x, we're going to have to use the chain rule, but I'm going to touch that in a sec. First I'm just showing you, so I'm going to touch on that and show you why it's actually really elegant, why you can easily find the derivative of y not knowing, how you can express the derivative of y or any function of y without actually knowing it. Okay, so we have the following equation here, and it does look a bit long, but we just work out the things. So we have 2x here, because that's the derivative of x squared, and then something, and then because r squared is a radius, it's just a constant basically. So the derivative of a constant, regardless of if it's to the square power or to the power of 100 million, whatever, it's still going to be a constant. So there's no rate of change, so therefore it's 0. Actually, that's meant to be an equal sign. That's equal to 0. And then what do you have here? What you end up having here is you just work out the derivative of this expression as if y was like x. But then what you do is you add to your paper, you just write dy over dx times dy. And the reason why is because y is a function of x. So essentially, you can do a little trick there and essentially assume that y is a composite function here. So when you work out this derivative, you work out the dy over du times du over dx, and the u in this case becomes x, because x can be seen as the internal kind of function. And really, it's just, you don't even know too much about this. You just, every time you see d over dx of any expression with respect to any expression written in terms of y, you just know that you work it out as if it was x and then times it by that symbol dy over dx, which is basically the derivative. So that's great. So we said that we can use algebra in this. And what we do in algebra is we rearrange equations to find the subject. So what's the subject we are looking for here? We are trying to find dy over dx, because that's a derivative, and we are trying to find the derivative from this implicit function. So just like we do in regular algebra, we essentially we minus 2x from both sides to get rid of this. And we end up having the following expression. And now we know that we can divide both sides by 2 to simplify things. So we have y times dy over dx. And by the way, this is not really a fraction, although sometimes in differential equations it does act as a fraction. But I'm not going to touch into that. I'm not going to get into that, because that's a really philosophical question. Is the derivative symbol a fraction or not? But for now, just know that unlike algebra, we cannot use the method of say multiplying by dx in both sides. That just doesn't work. So what you are really looking at when we say implicit differentiation is actually just using other algebra methods. So just differentiating sides and simplifying expressions till we get what we want. So then what you have here is minus x. And so that's easy. Dy over dx is equal to dividing both sides by y minus x over y. And that's it for this video. I am going to continue this video because, I'm going to continue this topic in the next video because I want to discuss inverse functions for those of you who are doing A-level further maths and AP calculus AB. I don't know about AP calculus BC, but I know that AP calculus AB definitely does teach inverse functions. So see you in the next video.